Okay. I have an hour to work on this before I go to work. I actually would have spent a little longer on this, but one of my favorite YouTubers, maybe my favorite YouTuber, posted a new video, and I had to watch it. Anyway, so what I have been able to do here is, oh yeah, this set point, this was misguided. I guess I did a lot of this off camera. Yeah, this read bias is also misguided. I'm just going to delete it here. So I have two functions here, RREF and TB. I couldn't think of a better name for this. But what all of this does together, I eventually debugged it and got it working, is, well, here, how do I do this? Like that. Yeah. So say you have a system like this. I actually took out the torques from my solution vector. I decided to simplify things that I wouldn't allow holds to apply a torque on the dude. Anyway, the point is, if I want to have a matrix times a vector equal another vector, I usually have infinite solutions for this. Now, why is that? Well, because right now the only conditions I'm enforcing is that the sum of forces and the sum of torques equals 0. So actually that's something I also did off camera, so I can briefly explain that. I mean, I won't go into details here, but I have this function here called make static equations, which makes a matrix A and a vector B such that the solution x to ax equals b is all the forces on each of the holds. And right now I'm assuming 4 holds. I'm just trying to get something up and running here. Okay, now this matrix A, so the first index is the equation number, right? And so the second index is which of the state vector components or solution vector components is used. So here all this is saying is that 1 times f0 in the x direction plus 1 times f1 in the x direction and so on all add up to 0. Notice that I don't set, so I default this vector b here to 0, and I don't set the b 0 component so it stays at 0. In other words, the sum of all these forces is 0. Makes sense. Same thing for y, and same thing for z, except I define z to be the upwards direction here, and that has to account for the weight of the dude. Without going into too much detail here, I wrote out all the equations as well for the torques or moments or whatever you want to call it. I just decided to do it around the origin because it led to the simplest equations. But ultimately, what that gives me is 6 equations and 12 unknowns. Now, there are other constraints that we could impose. Some of them actually could go into this matrix, and I may do that. Some of them don't. So for example, if we wanted to model the holds more accurately, we could say, oh, well, if your, so let me try and draw a picture of this. Oh, shoot, wait, man, I shouldn't have started the stream. There's something, shoot, I have like a, okay, I have like a 2-minute thing to do here. 1 second. Yeah, let's zoom in on that. Shoot, I shouldn't have started. Okay. And now I'm ready to go. So, okay, so what I was saying earlier is, where's my drawing? So what I was saying earlier is, this is an undetermined system. There are other constraints that we could add. So, like for example, one easy constraint to add, this is something you might have if you were working on like a textbook problem, is you could say, oh, well, assume that these holds can only apply force upwards or something like that. I don't know. But I actually need to deal with some more complex constraints that I don't have any obvious way of casting into this matrix times vector form. So for example, let's say that, let's take this one for example. Now, these two drawings, I didn't just draw them randomly. I actually kind of had a goal in mind here. Is, let's say that this hold is applying force that way, this hold is applying force that way, and so on for all the other holds, right? Well, and of course your mass, which I'm just modeling right now, is being all around your navel. So because of all these forces, there is a shear force and a bending moment at every point on your body. I'm not overly concerned with the shear force right now. I don't think I'm going to create a situation where the body is going to shear itself in half. But the bending moment I care about, and in particular, I care about the bending moment at the elbow joints. That's like the number one bending moment that I care about. It's not the only one. But the reason is because any bending moment that gets applied at your elbow joint necessarily is because you're engaging your arm muscles. And one of the first things you kind of learn when you're climbing is that your arms get tired really fast, right? So for example, one constraint, or maybe it's not exactly a constraint, but maybe one optimization goal would be to find the forces and directions of the forces on the hold such that it minimizes the work that your biceps have to do, right? That's one idea. But obviously, if we optimize just the work that your biceps are doing, we may actually create a situation where another part of your body is working really hard. So what I'm trying to get at finally is that the next set of constraints is I pretty much need to assign a score to a particular set of forces on the holds, and I'd like to minimize that score. I think that's the most general way for me to move on. By the way, there are some cases where I might add like actual constraints. So for example, I'm not going to do this like anytime soon, but in the future, maybe I'll have a situation where like, okay, well, this H1 isn't just like a thing that you grab onto. Maybe it's, you know, one of these classic, like, let's see if I can draw it. It's one of these classic, like, little tiny holds like this, right? And let me draw like a hand for scale. Not so good at drawing hands, especially with a computer mouse. Oh man. Well, whatever. I'm not winning any prizes, but so like these little tiny holds like this, you pretty much can only get forces in certain directions. And also, you know, we may have a coefficient of friction here, which means that, yeah, maybe you are, your normal force on this surface is like this, but then the coefficient of friction isn't good enough for you to stay on. Or to say it more directly, there may be like upper limits on these forces, depending on the directions and stuff like that. So that's something that I kind of do need to do at some point in the future, but I'm not doing it now because that is way too complicated. I just need to make sure that whatever solution I use doesn't make it impossible to add in those kinds of constraints. So yeah, basically that's what's going on. I have this matrix which is underdetermined. I eventually found a way of taking this matrix S and this vector V and breaking it down into this T and B. And this T is actually the basis. It's the column vectors of T is the basis of the null space of S. And this B vector is just one particular solution to S. It's one particular assignment to the forces that satisfies the original equation. Of course, there's an infinite number because S is underdetermined, and the entire set of solutions is completely determined by this formula. We can add anything from the null space to this one particular solution to get any of the valid solution vectors. So yeah, we have this, in principle, the way I've drawn it here, three-dimensional space, and then in practice, at least in my current implementation, I have 6 equations and 12 unknowns. So I have a 6-dimensional space, and in principle, I could get any vector from that space and assign it a score. And some of them may be invalid. So once again, like, okay, if you have like a really smooth hold, there may be some force vectors that are impossible on it because the coefficient of friction and the normal force, yada yada yada, stuff like that, right? What we have, I'm sort of being a little long-winded here, but it's partly because, you know, I didn't write a script before I started, and that's just always going to happen when you don't have a script. Anyway, we kind of have like a... Come on. Not close enough. We kind of have like a solution space. Let's suppose that the solution space is two-dimensional. So we have a solution space where, like, you know, maybe we have a local min. I'm just going to draw it like this. Right. So maybe we have a local min for the score. So this is score. Also, I don't like this font. This is, I'll just call them x1 and x2 for the dimensions of the solution space, right? Now, actually, maybe, you know what, I'm just going to erase this for a second. I'm going to draw it as a contour plot. Well, I guess x1 and x2 can be negative, but whatever, you get the point. X1 and x2. So we may have, like, you know, maybe this region is invalid. You know, maybe this region is invalid. And, you know, maybe we have contours that look like this. Right, and let me make these red. So maybe this is invalid solution. So in principle, this score graph, right, has these random bits that you can't even go into. And we could have local mins and global mins and all that stuff. So we need a way of probing this solution space and finding a reasonable winner, right? Well, yeah, that's the task that we have to solve today. So the obvious way of probing an n-dimensional space to find a minimum is Nelder-Mead. I've never coded it before, but I have a basic idea of the method. Of course, Nelder-Mead kind of doesn't work that well if you have these maybe arbitrary pockets of invalid solutions. So maybe I need to make some modifications to the Nelder-Mead method to understand this. Another method could just be like random probing with gradient descent. So maybe what you could do is put a bunch of random points. Whoops. Right, just randomly probe the space, or maybe not even randomly, maybe just uniformly, right? And then for each point, like kind of follow gradient descent. So that one would go there, this one would go there, this one would go there. Let's just say for the sake of argument that this kind of tends that way and then dies. This one goes there, right? Maybe say that one dies and then this one just dies immediately. So that's another idea. Now, if we're going to do random probing or even uniform probing like this, it would be nice to have bounds on the total solution space. And actually, we can obtain those kinds of bounds. This is classic matrix norm theory. So basically, if we impose a maximum norm on the forces, then that gives us a maximum norm on this null space vector, right? So in other words, if we impose a maximum on this norm, then that implies a maximum norm on this vector, right? And that maximum norm on this vector is determined based on the maximum eigenvalue of this matrix. At least I remember that much from Linalge. Actually, I didn't learn that in Linalge. I learned that in a controls course. Anyway, what time is it? How much time do I have? Okay, I'm still okay for time. So I guess that's what I'm going to try and do today, is I'm going to try implementing maybe gradient descent and yeah. So well, I guess that's what we're gonna do. So I guess that means I need a score function, which is a little more complicated. But you know what? We can start with a really simple score function just to get us started, just to be able to try stuff out. And that score function could be the norm of the force vector. So yeah, let's just pretty much do it. I guess right before we start, let's do a little bit of math to get an idea here. So we have some score function. So score equals f of, I'll call this capital F for my solution vector. And I know that f is equal to t, my null space matrix, times my vector that I'm searching, x plus b. So the derivative of score with respect to xi is equal to the derivative of f with respect to f times the derivative of f with respect to xi, which is I gotta think about this. So I'll just call this, well, I may as well call it f1x, f1y, f1z, f4z. This is equal to, I gotta do this or else I'm never gonna understand it, right? So I'll call this T11, T12, T13, T21, T22, T23, all the way down to T12. Let's call it N1, TN2, TN3, times x1, x2, x3. And if we want to take the derivative, I see. We need the multi-dimensional chain rule here. That's right. So this is actually the sum over I of, actually I can draw this with the pen, so I'll leave space for it. The sum over I of df by dfi times what's dfi by d, sorry. So I'm going to call this k. And what's the derivative of dfk with respect to dxi? Well, that is tki. And actually, I'm just going to call this j so that it matches my normal usage of indices within a matrix, and then I will call this I, like that. And so, yeah, this is the sum over I of df by dfi times dfi, so let's say it's this one, dfi, well, let's say it's this one because I actually have it in the matrix, by dxj, so ij, like that, right? Okay. Now, in principle, I actually can't compute this. I mean, I can right now because I'm choosing my score function to just be the Euclidean norm, so actually I actually could compute this. But in principle, I can't compute the derivative of this score function. I'll probably just have to approximate it by probing nearby or something. Right. Yeah, so actually, if I rewrite this as a matrix, that is TKJ. Oh, sorry, this should be an I. So that is the sum over one row of T times the derivative of this. So it is just T. Oh, no, wait a minute. So actually, I think the complete derivative, or I think what I mean to say is with the Jacobian. I think that is what I want there. The Jacobian of score with respect to, well, whatever. Let's just call it like this. You'll know what I mean, right? Dx is equal to, I think, so the sum over I. Oh no, that's going down a column of T. Wait, hold on. No, it is going across a row of T. Wait, no, hold on. The derivative of score with respect to xj, let's say it's x3, is the sum of, Yeah, you do go down a column. So it is T transpose times D F by dF. I think. Is that right? Because if I take just one component, it is equal to this times the derivative of this and add them all up. So yeah, I think that's right. Okay, great. Right. So this is actually the gradient of the score. With respect to x, I guess I need to write, so, which is what we care about. So we need to implement this. Yeah. I'm just thinking here about how I'm going to implement this. And actually, this is gradient of f with respect to f. Okay? Does this make sense at all? Let's ask Wolfram Alpha. This is work. Actually, maybe this is a better question for Google. Now, what is the Hessian? I keep seeing this word. Anyway. Yeah. Yeah, it is A transpose times the gradient. I was right. Okay, good. That makes me happy. Well, alright, well, Wolfram Alpha wasn't that helpful. Okay, so we have confirmation that this is actually on the right track. So, how do you get the gradient? Well, for now, I will actually just use the fact that I am using the Euclidean norm as my score. How will I do it later on? I guess I'll just need to approximate it numerically. that seems tricky. Because, like, so the way to approximate the gradient is just walk a little bit in every dimension, and, well, that's it, right? But how far should your step size be? You know what? I actually do want to start with this problem because I just had an idea. So let's say that we wanted to approximate the gradient at this point here. Then what we could do is take a little step that way and find the df by dx, and take a little step that way and find the df by d. Well, I guess I called it x2 here. But we have a question to answer, which is, well, was that step too big? And we don't want the step to be too small because then we'll have numerical accuracy problems. So here's my idea. Let's draw this again, but in one dimension. Let's say that we have some function here. I guess I can do this. The classic crazy function that calculus professors draw in Calc 101. And we want to approximate the gradient. Actually, let me pick a more interesting point. We want to approximate the gradient at this point here. Here's the idea. Start with an arbitrary h, and then calculate the change in f over the change in x, and then also do the same thing at h over 2. And if those 3 points are close to collinear, then we're done. You know, we've done it. There can be some, obviously there can be some pathological cases where this doesn't work, but I think this is good enough for our purposes. Yeah. So here, if this is too big of a step, then we'll make it smaller, and until we get points that are roughly collinear, right? Let's implement that because that's actually pretty simple. So let's put it, I don't know, up here, I guess. Function approx gradient of f and x. So var, I guess v0 is equal to f at x, and let's start. I see. Yeah, that's right. So var g is equal to new array of x dot length, and I guess we may as well assert that x dot length is greater than 0 just for simplicity. So this is going to be the return value. Then we're going to do for I equals 0, I is less than x dot length, I plus plus, walk a small step along dimension I, and also walk by half of that step size in the same direction if those 2 points and v0 are collinear, then the slope is a decent approximation to the gradient. Okay, so let's do that. Var, let's call this x1 is equal to x dot slice. We will do var h is equal to, man, what do we start this? I guess we can make this a constant or something, but you know, let's make it 0.1. Like, I have no idea. Arbitrary. Let's make it 1e minus 3. And also, we do need to check for undefineds, don't we? So, is there a try-catch in JS? Oh, there is. Try. Just return. Well, what should we return here? Let's do a well, I guess we'll just return nan. Oh, you can just do nan. Okay. Can you do that in C? Actually, I'm kind of curious. C, create nan. Huh. Fascinating. Okay, anyway. So we're just going to return nan. This is what I need, like that. No. Actually, I think I should just return an empty array. So, okay, I think I finally figured it out here. Returns empty array if f could not be evaluated at x or within neighborhood of x. Okay, so okay. So then what we will do is we will do x1 of I equals x of I plus h. Now we will do var v1. Actually, let's call this x2. And let's also do do this in a while loop. Actually, let's do while h is greater than tall. So x2 of I is equal to xi plus h, and then var v2 is going to be f of x2 Ooh, actually, I just had an idea. X plus H. So I'm going to call this VR, and I'm also going to use VL. If, okay, so JS check for nan or undefined. So what happens if we do type of nan? That is a number. If I do type of undefined, okay, so if type of v0 does not equal number, return an empty array. If it's not a number or is nan. Okay, that works. Actually. A little bit of extra copying, but who cares? You know, I'm not concerned with speed right now. VL. And same thing for VR. And finally, we'll do try catch. I'm not sure about returning an empty array, but that's okay. We can change that later. Okay. Now, check if if those 2 points in V0 collinear are close to collinear, and the slope is a decent approximation to the gradient. If VL, V0, VR are close to collinear, so we're going to do var slope L is equal to V0 minus VL over H, and var slope R is equal to VR minus V0 over H. If 0.9998 times slope L how do you, what would be a good way of doing this? We want percent difference, right? But we got to be careful about dividing by 0. What am I doing? Oh my god. If slope math.abs of slope R minus slope L is less than, I don't know, I have no idea. Also, slope R minus slope L is VR plus VL minus 2V0. So if VR plus VL divided by V0, we'll do a math.abs on that. 2 times V0 is less than So let me explain what I'm thinking in my head here. Also, what time is it? Oh man, wow, the time went by really fast suddenly. Okay, I'm gonna just find a free spot to grind. No, no, no. So like, so I guess let me delete this stuff. So if I have like these 3 points like that, my idea is that, yeah, if the average of these 2 points is close to the center point, yeah, so the average is this plus that divided by 2, and then the difference is that minus that, or the absolute value of that minus the sum divided by 2. Yeah. So it's VR plus VL over 2 minus V0. But because divisions are, well, whatever, I don't care. By seeing how far V0 is from the average of VL and VR. So if that distance is less than, God, I don't know, 1e minus 5? Totally arbitrary. Also, there is a thing you can do in JavaScript, JS, continued nested loop. There's a really cool, this is a really deep like JavaScript thing. What is going on here? Yeah, isn't that cool? So, loop. And here what we're going to do is so let's do var average is equal to that. So if the average is close enough, then we will do g of I is equal to average over h, because this is equal to VR plus VL. Oh, wait, that is not correct. Equals VR minus VL over 2 times H. Okay, and then here we're going to continue the outer loop. And then here we will do H times equals 0.75, say. And then here, if we get out of this loop, then fails to converge. And we'll return something like that. Okay. So I guess we should try this out. So var So now let's do console.log approxgrad of distance at the point 2, 2, 3, just for interest's sake. Okay. What time is it? Ooh, I'm running out of time. Well, we got an empty array. So instead of returning empty arrays, let's return string with returns error message. Message if gradient could not be computed. Could not evaluate at initial point. Function returned invalid number. Could not evaluate in neighborhood. And then here we will do function, well, yeah. Oh, someone messaged me at work and it's probably bad news. Oh, okay, it's fine. I'll deal with that at 9, but I have to finish this first. Fails to converge. Okay, let's try that. Proximate gradient could not evaluate at initial point. So, right. Function emag vex return the distance. You know what? Okay. We'll go back here. Mag. Approximate grad function returned an invalid number. I've only got 5 minutes before I gotta go to work. Why is this Nan? What's going on here? I probably used the V or something. X. Oh, duh. So the approximate gradient is this, which, let me calculate the actual gradient for comparison, since I know what it is. So what's the gradient of the Euclidean norm? D by dxi of square root x dot x is equal to 1 over 2 square root of x dot x times 2xi, right? Yeah. So let's call this S. 1 over 2 square root of x dot x. The actual gradient is S times 2 times 2, S times 2 times 3, right? So these should be pretty close. Oh, wow, that's really quite good, actually. We got like 6, even 7, almost 7 digits. That's really good, actually. I'm happy with that. Okay, so we have an approximate gradient function, which seems to be okay, at least in this really simple test. Also, why did I put this here? So I don't have time, sadly, but the next thing I'm going to do is gradient descent using this approximate gradient function, which should do the trick. So we're going to do that, and then it should be a fairly simple matter to do random probing. Yeah, okay. Oh, it's 9, I gotta go to work. Anyway, but I will leave a little note for myself next time. Implement gradient descent using the approx grad. Do some kind of random probing, and then find solution to statics equation with least norm. Now, actually, I happen to know that using the Euclidean distance, or like the norm function, using the norm function should only have one global min. I mean, is that true though? Well, anyway, it doesn't matter because we're going to use approximate gradient, but yeah. All right, I gotta go. Too bad.